So gravel is being dumped from a conveyor belt onto a right circular conical pile. You measure that the radius of the base of the cone is 3 times that of the height of the cone. You also measure that the cone's height is increasing at a rate of 3 meters per minute when the radius is 2 meters. How fast is the gravel being dumped onto the pile in units meters cubed per minute? This is a good one. So again, my artistic abilities must be astounding to you. This is a cone. Its height we'll call h, and we'll call its radius r. Now, what is given to us as far as rates are concerned? The cone's height is increasing. That's a rate of change. That means that our height, dh dt, the rate that our height is increasing is 3. Okay, good. What rate are we trying to find in this problem? Well, we're trying to find how fast the gravel is being dumped onto the pile. And that is a change, a gravel dumping onto this pile is a change in the volume of this cone. So we're trying to find dV dt. And as always, once we figure out which rate we're given and which rate we're trying to find, we need to relate those two variables, v and h, the volume and the height of this cone. All right, we know that the volume of a cone is 1/3 pi r squared h. It's 1/3 the volume of a cylinder, I suppose. And both the height and the radius are changing with respect to time, so this derivative is going to be fairly complicated. If we want to take a derivative of both sides of this equation, you'll notice on the right side here, we have a function of time here, and we have a function of time here. So when we take a derivative with respect to t, we're going to need to use the product rule. Now 1/3 pi is just a constant, so we could leave it out there if we want. And the product rule says we're going to take the derivative of this first term, which is 2r dr dt, times the second term, and we're going to add on to that the first term, that's r squared, times the derivative of the second term, dh dt. Now we look at this for a second and we see that we don't have everything that we need just yet. We're given dh dt, which is great. We're going to plug that in here. We're given that the radius, when we're looking for these rates, is 2. That's pretty good, so we're going to plug that in here. What we don't have is a rate of change of the radius or the height. But we are given that the radius of the base of the cone is 3 times that of the height of the cone. That is an equation that tells us that the radius is 3 times the height of the cone. Now we could differentiate this to get the r dt equals 3 dh dt. And now I think we're given everything that we need. Because we're given that r equals 2, we know that 2 equals 3h. At this moment that we're trying to relate our rates, we have h equals 2/3. And since we're given that dh dt equals 3, we now know that the r dt equals 3 times another 3, which is 9. Okay, a little bit of sloppiness there, but we're going to plug in dr dt here is 9. We're going to plug in h equals 2/3. And we know that r here and here is 2. And we know originally that we were given dh dt equals 3. All right, let's plug in everything that we have here and see what happens. Okay, so that took a little while. I plugged in everything that we knew here, and now we just need to simplify, reduce. 2 times 2 times 9 times 2 is 72. 2 squared times 3 is 12. We can find a common denominator on this 12. And in the parentheses here, I am getting 108/3, which we can multiply by the 1/3 to get 108/9. If we want a little bit of closure and get maybe something close to a real world number here, I'm getting that this is approximately 37.7. And a unit check here, we are talking about meters cubed per minute. Okay, so the volume of that conical pile is increasing at a rate of 37.7 meters cubed per minute. That's how much gravel is going onto that pile. Okay, I think that's going to do it.